This lecture video will cover colligative properties. Please read the OER textbook chapter section 11.7 for more details. When we talk about colligative properties, we are looking at the changes that caused by when a solute is added to a solvent and is changed the physical property of the pure solvent. Listed here are examples of colligative properties. So when you have solution that contains solute, it's going to cause the vapor pressure and freezing point to be lower than of the pure solvent. Okay, and when you're looking at boiling point and osmotic pressure, the solution would have higher boiling point and osmotic pressure than of the pure solvent. The next thing we are going to take a look at is we are going to take a look at the application of colligative properties, more specifically the freezing point depression. Okay, so here are some examples. Okay, so the first picture that you see here shows antifreeze. Antifreeze contains water as solvent, and the solute in antifreeze preventing water to freeze during winter by lowering freezing point of water. The second picture shows liquid deicer, which rely on the same principle as the first picture. The solute in liquid deicer prevents water to freeze at its normal freezing point. This effect is the same as when salt are sprayed on icy road as well. Same idea also apply in the process of making ice cream as well. So ice cream contains many solute that its freezing point is going to be about 27 degrees Fahrenheit or below 0 degrees Celsius. So to freeze an ice cream, the temperature of ice need to be colder than the freezing point of ice cream. So to achieve the colder temperature, salt is added to the ice to reduce the temperature of ice in order to freeze ice cream. The last picture shows frozen frog. This frozen frog is still alive because glucose in its blood and cells prevent water in its body to freeze. Without glucose, water in frog's body would freeze and that would rupture itself. These are just few examples. In real life, there are several more applications of colligative properties. The next thing we are going to take a look at is we are going to take a look at the concentration units that use in colligative properties. Because colligative properties depend on amount of solute and also is related to the temperature as well as you see as the boiling point and freezing point, right? So the unit that we are going to use is going to involve with mole and is going to have to be independent from temperature as well. So the two units would be the mole fraction, which is going to be the mole of a certain substance, right, divided by the total mole of all component. Okay, so this mole fraction here, you can use it as in terms of mole of solvent or mole of solute, right? So, and then you are going to divide that by total mole of all component within the solution. The second unit that we are going to use is molality or molal. This unit is going to be used instead of molar concentration because this unit is going to be independent from temperature. Why is it independent from temperature? Is because if you're looking at this, right, all of this involved with the amount of the substance, right? So mole and kilograms, right? So mass and the number or the amount of molecules, they are not going to be dependent on temperature. As the temperature change, all of these are going to stay as it is. Okay, so it's not going to be like when we talk about molarity, right? Big uppercase M, this is equal to mole over liter. As you see, the volume of the substance is going to depend on temperature, right? So as we learned in chapter 8, right? So as temperature increase, the volume also going to increase as well, right? Because the substance is going to expand, right? Because the kinetics energy going to be higher, molecule move faster. However, when the temperature decrease, right? The substance is going to contract, so the volume is going to decrease. So that means in this case, molarity unit, we're not going to use in this colligative property because it depends on temperature. So we are going to use only molar concentration and mole fraction in this case. Okay, so that means in this case, in order to understand this more, you will need to make sure that you know how to convert into mole fraction and also to molar concentration as well. Note that molar concentration is the lowercase m italicized. Okay, so italicized lowercase m. So to clarify, okay, so we have several units that involve with m. Okay, so this uppercase m, this is molar concentration, okay, which is mole per liter. Okay, and you have lowercase m that is not italicized. So this is referred to meter. Okay, and then if you have lowercase m but italicized, this is going to refer to molar concentration, okay, which is mole of solute per kilograms of solvent. Okay, so you need to know these two units. Okay, so these two units will not be given on the exam, so you need to know what they mean. So if you don't know, jot it down in your note card. Okay, so so that way you know how to solve for those. Okay, so another one that you might be wonder, what about, we have another M that is milli. How are these different from any of this? Okay, so milli is going to be lowercase m that is not italicized. Milli is the prefix. So that means it can come before any of this. For example, it can be millimolar, right? Or millimeter or millimolal. Okay, so it can be any of those. So again, so these are the M letter that involved with the unit and prefix. Okay. All right, so since we are talking about different units, so now we are going to need to learn how to convert them into specific unit, right? So let's take a look at example 1. Okay, so example 1, we are given a solution, an aqueous solution. Okay, so that is prepared by dissolving 50 grams of sucrose. Okay, so and the final volume of this solution is 355 milliliter. And it's also giving us density of the solution as well. Okay, and it's also giving us the molar mass of the solute as well, which is in this case is going to be sucrose, right? So if you think about this, because it's an aqueous solution, so that means our solute would be sucrose and the solvent that we are using is going to be water. Okay, so the first one, I'm going to start with the unit that you are familiar with that we cover in chapter 11.5. Okay, so molarity or molar concentration. Okay, so this is going to be the uppercase M. Okay, so in order to calculate for this, we know that molar concentration is mole of solute per liter of the solution. Right? So I'm going to start with that. So that means in this case, in order to find out molarity, we need to know mole of solute. So the first step would be find mole of solute. Okay, so you are going to use the grams of sucrose, which is going to be solute, right? It's the minority. You are going to divide by its molar mass, then you are going to obtain mole. Okay, for a liter, this is the liter of the solution. We already know, right? It's given that the fact that the volume of the final solution is 355. So this 355 milliliter is the volume of the solution. So you need to find that into liter, right? Because molarity is mole per liter. So convert that milliliter to liter by divide by 1,000, right? So you are going to get 0.355 liter. So to get the unit molarity or molar concentration, you are going to do mole over liter, and you are going to get 0.415 mole per liter as the final answer. So again, you can answer in mole per liter like this, or you can just leave it as uppercase M. So either way is the same. Okay, so these two units are referred to as molar concentration. Okay, so now the next thing we are going to take a look at is, so this one, you already know how to do this, right, in chapter 11.5. So the next one we're going to take a look at is, how can we calculate for molar concentration then? Okay, so molar concentration is going to be mole of solute per kilograms of solvent. We already know mole of solute, right? So we calculate that from the beginning, from convert grams of sucrose to mole of sucrose. So we already know that. The next thing we need to know is we need to know kilograms of the solvent, right? So, so what we're gonna do is that we need to find kilograms of solvent. So before we do that, think about this first. Okay, so if you read all of these, we don't know the solvent, right? So we know only the solute. Okay, we know only the solution. So that means in this case, in order to find out the mass of the solvent, you need to subtract the mass of the solute from the solution, right? So if you think about this, right, if you have a beaker, you make a solution is going to contain solute plus solvent, right? So all of this is what we call solution. So that means we know solution, we know solute, then you should be able to find out the solvent, right? But if you're looking at this solution that is given, is actually given us in terms of volume. Okay, so it's giving us in terms of volume. The solute that we know is in grams. So that means these two, you cannot subtract them because they are in different units. So the first step is going to be, you need to convert these milliliter to grams first. What is the value that is going to allow us to do that? Well, if you read the given information, you will see that the density is going to allow to convert from milliliter to grams, right, of the solution. So that means in this case, what you are going to do is you are going to convert milliliter to gram using the density of the solution. Remember, this is the solution, so that's why I'm able to use it to convert from milliliter to grams. Okay, so in this case, what you are going to do is you're going to start with 355 milliliter of the solution. And you are going to use the density of the solution, which is 1.05 grams of the solution over 1 milliliter. Convert that, you are going to get 372.75 grams of the solution. This is of the solution, it's not of the solvent. In order to find out the solvent, you are going to need to do solution minus the solute. So in this case, it's going to be 372.75 minus 50.4 grams. Then you are going to get grams of the solvent. But molar concentration is per kilograms of the solvent, not per grams. So therefore, you are going to do one more step, which is convert that grams into kilograms. Okay, so now you get kilograms of the solvent already. All you need to do next is going to divide mole by the kilograms of the solvent. You are going to get molar concentration equal to 0.457 mole per kilograms, or molar concentration. Again, the reason why we are doing molar concentration is because this unit here is going to be temperature independent. It doesn't depend on temperature, but molar concentration, this is going to depend on temperature. Okay, so as temperature change, this value right here is going to change for molar concentration. All right. The next one is the mole fraction. Okay, so mole fraction, if we're looking at mole fraction of sucrose, you are going to use mole of sucrose over mole of the solution, right? So, and we know that solution is coming from solute plus solvent. So all you need to do is you need to pretty much find more of the solvent, right? Because you already know more of the solute, right? So you know more of solute from this step. Okay. So how do you find out more of solvent? Well, we just find out the grams of solvent earlier, right? So this is the grams of solvent. So all you need to do is that you use gram of the solvent and then divide by the molar mass of the solvent. What is the molar mass of the solvent in this case? Well, it said aqueous solution. So that means in this case, it's going to be molar mass of water, right? So you are going to use molar mass of water and you're going to convert that grams to mole. It's going to give you 17.89 mole of solvent. Okay, to find out mole fraction, all you need to do is that you are going to use mole of the sucrose, right? Because it's asking for more fraction of sucrose, divide by the total mole. So add more of sucrose together with more of water, you are going to get the total mole. And that is going to come out equal to 0.00816 mole fraction for the sucrose. All right, so let's take a look at example 2. So example 2, in this case, I'm going to let you try to complete this on your own first before you check your answer against my answer. Okay, so let's pause the video and then attempt this on your own. And then when you're ready, resume the video again to check your work. Now let's check your work together. So example 2, in this case, we are looking at the IV solution, right, of the 0.56 molar aqueous solution of glucose. Okay, so it's giving us density again. Okay, so that means in this case, this density here is going to refer to the density of the solution. Okay, so it's also giving you molar mass of glucose as well. Okay, so first we need to find out molar concentration, and then we're gonna find out mole fraction and also mole fraction of both glucose and also both water as well. Now let's take a look at one unit at a time. Okay, so when we're looking at molar concentration, by definition, molar concentration is equal to mole solute divided by kilograms of solvent. So that means in order to find out molar concentration, we need to know mole of solute and know kilograms of solvent. Okay, the second unit is mole fraction of glucose. So in this case, you are going to use mole of glucose divided by the total mole. Okay, so mole fraction of water is going to be mole of water divided by the total mole. Okay, so one thing I want to emphasize is that because these two are related, remember when you have a solution, right, you have solute plus solvent, and this is going to make up the solution. So that means if you're looking at the fraction, right, you are going to, so the fraction is out of 1. So that means if solute is equal to a mole fraction of X, the solvent is going to be 1 minus X, right? So similar to percent, right? So if you think about this, right? So if you have, let's say like 30% of solute how much solvent would be in this solution? Well, the solvent would be what, 70%, right? How do you get that? Well, it's going to be 100, right, minus 30%, right? So that means if you know percent of the solute, right, you should be able to find out the percent of solvent by subtract that from 100%, right? So same thing, but in this case, we are looking at fraction, so fraction have to be out of 1, right, instead of 100. Vice versa, if you know the mole fraction of solvent X, right, your solute is going to be 1 minus X. Or in other words, if you know how many percent of the solvent, the solute would be 100 minus X%, right? So it's going to be that. So that means in this case, in order to calculate for each of these units, we need to know mole of the glucose, right? And also know kilograms of the solvent, which is water. And also we need to know mole of water as well. Okay, so let's take a look at each one of these. Okay, so let's look at the definition of molar concentration first. Is given to us. Okay, so molar concentration tell us that in 1 liter, right? Because mole per liter, in 1 liter of the solution, we have 0.556 mole of glucose. That's what it means, right? Molar concentration is mole per liter or mole of solute, right, per liter of the solution. So that means in this case, we know that in 1 liter of the solution, there is 0.556 mole of glucose. The next thing that we can get from the given information would be the density, right? So the density would allow us to convert from volume to mass. So in this case, we know that 1 liter of the solution, right? If we want to know the mass of the solution, then you can use the density to convert to grams. But remember, the density is given in milliliter. So therefore, you need to convert this liter to milliliter first. Okay, so and then you use density to convert to grams. Okay, so that means in this case, we know that in 1 liter of the solution is going to equal to 1,040 grams of the solution. Okay, so this is the mass of the solution. So now, up until this point, you will see that I cannot plug into this equation yet. The reason for that is because we know more of solute, but we don't know the kilograms of the solvent yet. These grams right here is not grams of the solvent, it's still of the solution. So that means we need to find out of the mass of the solvent. In order to do that, right, so we know the solution comes from solvent plus solute. So in this case, in order to find out the grams of the solvent, you will need to actually find out the grams of the solute first in order to subtract from the grams of the solution. So what I'm going to do is I'm going to convert mole of the glucose that we know, okay, convert that to grams by using its given molar mass. Okay, so if you do that, you are going to get about 100.19 grams of glucose. Okay, so now you know grams of the solution, you know grams of the solute. So therefore, the grams of the solvent is going to equal to 939.81 grams. Up until this point, you are not able to plug into this equation yet because this one requires kilograms of the solvent. So the next step would be convert these grams into kilograms. It's going to give you 0.93981 kilograms. So now we know more of solute, right? We know kilograms of solvent. So now you should be able to find out molar concentration. Okay, so divide those two together. Okay, so if you're looking at mole fraction, okay, so mole fraction of glucose, we know more of glucose, but we don't know the total mole yet. So that means in this case, in order to find out total mole, you need to know more of the solvent, okay, which is of water, right? So in this case, you are going to get the grams of the solvent, okay, and convert that to mole by using water molar mass. Okay, so this is molar mass of water. So you are going to get 52.168 mole of water, okay, which is the solvent. Okay, so now since you know mole of solute, you know mole of solvent, if you add them together, you're going to get total mole, right? So since you know mole of glucose, you should be able to find out the mole fraction of glucose. Okay, so since you know mole of solvent as well, you can plug in mole of water, right? Divide by the total mole. You should be able to find out mole fraction of water as well. Okay, so let's put all this together. Okay, so for molar concentration, it's going to be mole of glucose divided by kilograms of water. Okay, so you're going to get 0.592 mole per kilograms. For mole fraction of glucose, it's going to be mole of glucose divided by the total mole. It's going to come out equal to 0.0105. Okay, so mole fraction, the unit will cancel out. So therefore, mole fraction doesn't have any unit. Okay, so mole fraction of water is going to be the same thing, right? So it's going to be mole of water divided by the total mole. So it's going to come out equal to 0.981. As I mentioned earlier, right? So you can calculate it this way, or you can get the mole fraction of water by using 1 minus 0.0105, right, which is 1 minus mole fraction of the solute is going to give you the same identical value. Okay, so, or if you want to check your answer, right, so these two need to add up equal to 1, right? So these two add up need to equal to 1 because everything is out of 1, right, for fraction. So when you add solute and solvent together, it need to equal to 1, mole fraction of 1. All right, the next thing we are going to take a look at is we are going to look at each of the colligative properties. So first, we're going to look at vapor pressure lowering. For vapor pressure lowering, as the number of mole of solute increase, you are going to observe that the vapor pressure of the gas above liquid is going to decrease. So this is the additional slide that I'm going to post on Moodle. Okay, so let's take a look at this. So if we have pure solvent, okay, so when you have pure liquid solvent, eventually some of the solvent will evaporate, right? And some of them will also condense as well. When they reach the equilibrium, dynamic equilibrium, the pressure above the liquid, right? The pressure of gas above the liquid, this is what we refer as vapor pressure. Okay, so I'm going to use VP for short in this case. Okay, so in this case, if you have pure solvent, the pure solvent would contain a certain vapor pressure above the liquid. Okay, so when I talk about vapor pressure, I'm referring to the gas above liquid. And when we are adding solute into this pure solvent, there would be 3 scenarios that we are going to take a look at. The first scenario would be when you add the non-volatile solute into the solution. Okay, so that means in this case, your solute is not going to vaporize. It's going to stay as it is. Okay, so the second one that we are going to take a look at is going to be the solution that contain volatile solute, which means the vapor pressure of the solute is also going to contribute into the total vapor pressure as well. And the last example is going to be when you have 2 volatile solute that's dissolved in the solution. Okay, so in this case, both of the solute is going to contribute to the total pressure above the solution. Please note that these 3 solutions, their vapor pressure are going to be lower than the pure solvent. Okay, so that means in this case, if you have vapor pressure of the pure solvent is going to have higher vapor pressure than any of this. Now let's take a look at one scenario at a time. Okay, so I'm going to take a look at the non-volatile solute first. When you have vapor pressure of the pure solvent, right, and then you introduce the non-volatile solute, the non-volatile solute is going to interact with the solvent molecule in the liquid phase. Okay, so as it interacts, it's going to prevent the liquid molecule of the pure solvent to vaporize. So that means it's going to reduce the rate of vaporization of the solvent. So therefore, in this case, the molecule of the solvent above liquid is going to be less. When the equilibrium re-established, you are going to observe fewer molecules of the solvent in gas phase. Therefore, in this case, it's going to result in lower pressure above the solution. So again, vapor pressure of the solution decreases because solute reduce the rate of vaporization, but not the rate of condensation. So therefore, in this case, it's going to causing the vapor pressure to be lower than of the pure solvent. So how can we find out the new vapor pressure of the solution then? Well, we are going to use Raoult's law to help us to determine the vapor pressure above the Raoult's law state that partial pressure of the solution, right, or the vapor pressure of the solution is going to equal to the mole fraction of the solvent multiplied by the partial pressure of the pure solvent. Okay, so this is tell us about how much solvent that we have and how much is contribute to the vapor pressure, right? So that's what it's telling us here. So in this case, again, the P stands for pressure or partial pressure or vapor pressure. Okay, so X is going to be the mole fraction. Okay, so this equation right here is going to be given on exam. Now let's take a look at example 1. Okay, so example 1 tell us that to calculate the vapor pressure at 25 degrees Celsius of a solution containing this many grams of the solute and also this many grams of solvent, right? So how do you know this is solute? Well, because it's contain less amount, right? So that's why I know this is solute, right? This is contain more amount, so this is going to be our solvent. Okay, so in this case, we are going to assume that ethylene glycol is going to be non-volatile because it doesn't tell us anything else. Okay, so we're going to assume that this is non-volatile. Okay, so that means on the exam or even on the homework, okay, so if it doesn't give you the fact that the solute is volatile, you have to assume that it's going to be in the non-volatile scenario. Okay, so in this case, it's giving us the vapor pressure of pure water at 25 degrees Celsius as well, and it's this many torrs. So that means we know that this is involved with only one volatile solvent, right? And this is going to be non-volatile solute. So we are going to use the equation that we see earlier, which is the pressure of the solution is going to equal to the mole fraction of the solvent, right? Multiplied by the pressure of the solvent, of the pure solvent. Okay, so in this case, we know the vapor pressure of the pure solvent, right? And we don't know the mole fraction of the solvent yet. Okay, so if you know this, then you can find out the partial pressure of the solution. Okay, so that means the first step, we need to find out the mole fraction of the solvent first. Okay, so in order to find out mole fraction of the solvent, remember mole fraction of the solvent is going to equal to mole of the solvent, right, over total mole. So that means in this case, in order to find out total mole, you will need to actually convert grams of the solute into mole of solute first. Okay, so by add all this up together, right? So you're gonna get 62.007 grams. Okay, so in 1 mole, convert that to mole. So this is going to be mole of ethylene glycol. Now to find out mole of water, so you're gonna use grams of water, divide by molar mass of water, you are going to get this many mole of water. To find out mole fraction, it's going to be mole of water divided by total mole. So you are going to get mole fraction of 0.9467, which is going to be, so it's going to contribute a lot, right? So it's close to 1. Makes sense because solvent is water. So water is going to be majority component in the solution. Okay, so if you think about this in terms of percent, this is giving you equal to 94.67%, right? So that's a lot. Okay, so now if you want to find out the partial pressure of the solution, right, or the vapor pressure of the solution, you are going to use mole fraction of solvent, which is water, multiplied by the vapor pressure of water, which is 23.8 torr. You are going to get 22.5 torr. You might ask me, hey, do I need to change this into ATM? The answer is you don't have to, because the problem doesn't ask you specific unit for vapor pressure, right? It's just ask you to calculate vapor pressure. If you leave it as torr, you are going to get the final answer in torr. If you convert into ATM, you are going to get final answer in ATM. Okay, so in this case, again, the problem doesn't ask you a specific unit, so you can just leave it as torr, but you are welcome to change to ATM if you want to. Okay, so one thing I would like to mention right here is that, as you see, right, this is the vapor pressure of the pure solvent. This is vapor pressure of the solution. As I mentioned earlier, right? So when you have a solution, the solute is going to lower the vapor pressure of the solution, right? So it's going to be lower than the pure solvent, which is exactly what we expect, right? So vapor pressure here is actually come out to be lower than the vapor pressure of the pure solvent. So that's exactly what we expect, right? So this is the colligative properties. Now let's take a look at example 2. Okay, so for this example, I would like you to attempt this on your own first before you check your work against my work. Okay, so let's pause the video now and resume again when you're ready. All right, let's check your work together. Okay, so we have a solution contain ethylene glycol and water. Okay, so and it also has a vapor pressure of 7.88 torr at 10 degrees Celsius. Okay, so it's giving us that pure water has vapor pressure of 9.21 torr at the same temperature. It's asking us to find out mole fraction of ethylene glycol. All right, so in this case, I'm going to use because we know that this is involved with the vapor pressure of the solution. Okay, so this value right here, we know that is of a solution. So that means we know this vapor pressure. Okay, so what else do we know? We know pure water vapor pressure. So that means we know this. Okay, so that means what we need to find out is this mole fraction right here. Okay, so I'm going to go ahead, plug those in. You are going to get the mole fraction equal to 0.856. If your answer is 0.856, is incorrect. Okay, so this is incorrect. Why? Well, it's asking for mole fraction of the solute, right? This is solute, not the solvent. Okay, so that means in this case, there would be one more step that you will need to take. In order to find out mole fraction of the solute, you are going to have to subtract that from 1. Okay, so subtract mole fraction of the solvent from 1, you are going to get 0.144. Okay, so again, because if you add mole fraction of solvent together with the solute, it needs to equal to 1. So that means in this case, if we have this much of the solvent, the rest would be of the solute. Okay, so that would be equal to 0.144. And again, I want to point out this one thing here. As you see, right, we have vapor pressure of the solution is going to be lower than of the pure solvent, right, according to the colligative properties. Okay, so the vapor pressure of the solution is always going to come out lower than of the pure solvent. Now, to summarize what we just learned, right, if you have a solution contain non-volatile solute, you are going to be able to find out the partial pressure of the solution by using the mole fraction of the solvent multiplied by the partial pressure of the pure solvent, right? In other words, if you're looking at this, right, you can looking at how many components as well that can vaporize. So in this case, if you're looking at this scenario, you see that there is only one component that can vaporize. So that means in this case, you can say it as well that the partial pressure of the solution is going to equal to the one component partial pressure that contribute to the total pressure. Okay, so the reason why I'm using letter A, because we are going to looking at when we have more than one volatile component. Okay, so for example, if you have two volatile components, okay, so for example, your solvent is volatile, the solute is also volatile. As you see in this case, the solute is also going to contribute to the total pressure as well. So in this case, your total pressure of the solution is going to come from the addition of partial pressure of the both solvent and also solute. Okay, so all of them together. Now, what happens if you have more than one volatile solute? So in this case, both solute along with the solvent, they all contribute to the total pressure of the solution. So therefore, in this case, the partial pressure of the solution is going to come from the addition of all of those partial pressure, right? So for all of the components. So here's the summarize of the equation that you will be given on exam. Okay, so pretty much when you have one volatile liquid right in the solution, you are going to use just one component. If you have two, then you have to add them up together. If you have three, you can add them up together as well and so on, right? Because all of them are going to contribute to the total pressure of the solution. Okay, so let's take a look at example. Okay, so this example is when you have two or more volatile liquid. Okay, so let's take a look at example one. Okay, example one is tell us that liquid A has a vapor pressure of this many torrs, and also liquid B has vapor pressure of this many torr. So we know that both A and B have vapor pressure, so that means they both are volatile, right? So that means in this case, we know that we need to take into account both liquid A and B into the total pressure of the solution. Okay, so it's giving us mole of A and mole of B as well. Okay, so it's asking us what is the total pressure of the solution. Okay, so how do we do that? So what we are going to do is that we are going to use partial pressure of A and B add together in order to get the total pressure. Okay, so in this case, since we need to know mole fraction, right, how much it contribute, right? So how many percent of A exactly? So we are going to find out the mole fraction of A first by using mole of A divided by the total mole. Okay, so you're gonna get 0.52. Do the same thing for B as well, or you can do 1 minus mole fraction of A, right? So that's gonna give you mole fraction of B because these two add together need equal to 1, right? So you can do it this way, or you can set up mole fraction of B equal to 6.00 mole, right? Divide by 6.50 plus 6.00 mole. You can do it that way as well. It's going to give you the same number. So what we are going to do next is that we are going to multiply mole fraction of A by the partial pressure of A. So if you think about this, right? If you have 100% of A or pure A, this is going to be the pressure of A. But we don't have 100% of A. We have only 52% of A. So therefore, in this case, you are going to end up with less than 360. So the next one is going to be B, right? So you are going to do the same thing, right? So this is pressure of B, right? But we have only this many percent or this fraction. So you are going to multiply that to B. So if you add these together, you are going to get pressure of the solution come out to be 212 torr. Okay. So now think about this. If you're looking at the amount of mole fraction, you will see that this mole fraction of A, right, is making A to become solvent, right? Because A contribute the most, right? B would be the solute. Okay. So as you see, if you compare the pressure of the solvent, vapor pressure of solvent is still higher than the vapor pressure of the solution. Right, so exactly what we mentioned earlier, right, in terms of colligative property. When you're looking at colligative property, vapor pressure of the solution is going to be lower than of the pure solvent. Okay, so that makes sense. Okay, so that's how you check your calculation. All right, so let's take a look at example 2. So in this case, I would like you to pause the video and resume it again when you're ready to check your work. All right, let's check your work together. So in this case, you are going to end up with 2 volatile liquid again. Okay, so we're gonna have to find our mole fraction of A, right? And also you need to find our mole fraction of B. Okay, so, and then what you are going to do is multiply mole fraction of A by the pressure of A, and then add to mole fraction of B multiplied by pressure of B. Okay, so you're gonna get 291 torr. And check your work again. Okay, so let's check your work. So if you're looking at this, right? So this is our solute, right? Because it have less mole fraction. This is gonna be our solvent. Okay, makes sense. This is pure solvent. Vapor pressure is still come out higher than vapor pressure of the solution. Okay, so that makes sense. So that means your calculation is correct. The idea of different vapor pressures of substances in solution can be used in distillation process. For example, as you see in this picture here, is represent simple distillation. Simple distillation is used when components in solution have significant different vapor pressures. Let me explain this picture to you real quick. Okay, so this flask right here contains solution that has several components with different vapor pressure. Okay, so it's connected to the column that has thermometer stick to it to measure the temperature. And this column right here is actually connected to the condenser. Okay, so, and this is going to be the receiving flask. And this solution is going to be placed over the heat source. Okay, so what happened then? Okay, so let's take a look at this. As a solution being heated, the substance that have weak intermolecular forces is going to have high vapor pressure. So those substance is going to boil first. Okay, so as it's boiled, the gas is going to travel up the column and travel to the condenser. Okay, so as it's passing through the condenser, since the condenser is cool, it's going to cool the hot gas down and it's going to condense hot gas into liquid, right? So, and then the gas will become liquid. Okay, and then you are able to collect at the receiving flask. Okay, so that's what it means. And because substance have different vapor pressure, they are going to have different boiling point. So therefore, in this case, you are going to be able to separate them by looking at their boiling point. And when the solution contains the component that have significant difference in vapor pressure, the component will come out at different times. So you are able to separate. An example of the simple distillation application is going to be used in distilled spirit. Okay, so for example, in this case, if you want to separate methanol from ethanol, right? So what you are going to do is you are going to use the idea of their different of vapor pressure or the boiling point, right? So in this case, you will see that methanol has lower boiling point than ethanol. So that means when the mixture that contains both methanol and ethanol is being heated, methanol is going to boil first and is going to condense and come out first, right? So it's going to leave the ethanol behind. And once you finish collecting all the methanol, then the second component that is going to boil is going to be ethanol, right? So ethanol is going to boil, and then that's when you are going to be able to collect the ethanol, and then it's going to leave all other components behind. For the solution that contain the components that have slightly different vapor pressure, the fractional distillation is going to be used instead. The fractional distillation is going to be similar to the simple distillation. The only thing that's different is that we are going to introduce the fractional column. Okay, so the fractional column is going to help separate the component that have slightly different in vapor pressure by extending the time for the gases to travel. Okay, so as gases travel, if the gas doesn't have enough kinetic energy, right, so it's going to start to condense and it's going to fall back down here. So that means it's going to, those that have slightly different in vapor pressure, they are going to be able to separate by this extension of the travel time for the gas. The application of this can be used in coconut oil refinery, right? So for example, if you're looking at coconut oil, they have different type product, right? So some are liquid and some are solid, right? So these are coming from the difference in the hydrocarbon or the number of carbon and hydrogen within the chain of the coconut oil, right? So those are liquid would be the one that contain medium chain triglyceride. And those are solid is going to be the one that contain long chain triglyceride. Okay, so as you see, as a number of hydrocarbon increase, right, you are increasing the dispersion force, right? So that means in this case, this long chain triglyceride is going to hold to each other strongly. So therefore, it's going to prefer a denser state, which is going to be like more like of the solid state, right? So in this case, as you see, right, so they have different strength of the IMF. So therefore, it's going to have different of the vapor pressure as well. So that is going to allow us for separate them. So in this case, if you do the fractional distillation, the medium chain triglyceride is going to come out first. Okay, so those are going to be the one that you are going to observe as the liquid, right? And then and those long chain triglyceride that are not able to vaporize because they have a strong internal forces, they are going to be left in the round flask. The fractional distillation can also be used in crude oil refinery as well. So based on the size of molecule, right? So they are going to have different IMF and they are going to end up with different boiling point or different vapor pressure. As you can see here, right, the small molecule would have lower boiling point. They are going to have higher vapor pressure. So they are going to travel up to the higher point in the distillation tower, right? And then they are going to come out in a the top part of the distillation tower. Whereas the larger molecule, right, they are big, they have higher boiling point, they are not going to be volatile. So therefore, they are going to stick around in the bottom or the lower section of the distillation tower. And then eventually you are going to be able to separate them in terms of the length of the hydrocarbon chain.